Okay, we've moved into section 4.3. We're still in chapter 4, of course, applications of derivatives. And in this section, we're talking about monotonic functions and what is called the first derivative test. So a monotonic function is a function that is either always increasing or always decreasing. And as a corollary to the mean value theorem here in corollary 3, it's hopefully it's easy to see that if the derivative is always positive, right? If f prime of x is greater than 0 for every point in an interval a to b, then f is always increasing, because the only way you can have a positive sloping tangent line is if you have an increasing function. Likewise, if the derivative is negative, less than 0 at every point in an interval, then f is decreasing on that entire interval. In other words, the only way you can have a negative slope to your tangent line is if f is decreasing. Okay, so then we can extend this idea to a test for the presence and nature of local extreme values. This is called the first derivative test. Essentially, you can read that, but it's also kind of descriptive throughout this picture. All right, if I have, let's say, for example, in this guy right here, where I have a local max. Now, we know that the derivative is equal to 0 at this local max, or it doesn't exist, right? Because here's another maximum example where the derivative doesn't exist or is undefined. But I check to the left and to the right of where that derivative is 0. If to the left of it the derivative is positive, that means it's an increasing function. And if to the right of it the derivative is negative, that means we're decreasing. So we were increasing up to a maximum and then decreasing. And you have the reverse here at a local minimum, right? At a local minimum, you have the derivative being negative, which means you have a decreasing function, down to a derivative being 0, a 0 slope, and then after that the derivative is positive, which means it's increasing. So if we're decreasing and then we have a 0 slope and then increasing, then we have a local minimum. And then the same thing happens on either side of critical points where the derivative is undefined. Now, some places we do have a derivative being 0. We have an instantaneous point, one point where the derivative is 0, but the function's derivative was positive before that, and then the derivative is 0, but then the function is still, its derivative is still positive, which means it's increasing. You hit a little plateau for just one value of x, and then it's increasing again. That is neither a local max or a local min. So the first derivative test says check the first derivative on either side of a critical point and see what that critical point gives you, a local max or a local min or neither. So example 59. Let's find the critical points of f of x equals x cubed minus 12x minus 5, and then identify the open intervals on which f is increasing and on which f is decreasing. So if you take the derivative of that, it's a simple derivative, right? Just power rules, 3x squared minus 12. Set that equal to 0. There's certainly no place where that doesn't exist. So the only time we're going to have critical points where that's equal to 0. So that's easily factorable, that quadratic, into x plus 2 times x minus 2. So we have two critical values, x equals minus 2 and 2. So the way to conduct the first derivative test is to set up a number line, write your critical values. So below that number line, I'm going to write x values, and above that number line, I'm going to write the derivative, f prime of x values. So at the critical points, when x is minus 2 and 2, we know the derivative is 0, so I wrote 0. Now to either side of the critical points, I need to check what's going on with the derivative. And the derivative will only stay the same, so I only have to check it for one value. So notice I'm going to check it for x equals minus 3 to the left of minus 2, then check at x equals 0 between minus 2 and 0, and then check at x equals 3. I've chosen values of x which when plugged into the derivative make them easy to figure out. So f prime of minus 3 ends up being 15, which is positive, so I come over to my number line and I write a bunch of little positive signs which indicate to me I have an increasing function. I draw an arrow up, reminding myself I have an increasing function. Then f prime of 0, what's the derivative of x equals 0? I get negative 12, which is a negative number. So I put a bunch of little minus signs to remind myself the derivative is negative everywhere in that interval. And I put a little down arrow indicating to myself, okay, that negative derivative meant decreasing. Likewise over here, I checked the derivative at 3. I got 15, which is positive, so I got a bunch of positive signs indicating the derivative is positive everywhere where x is greater than 2. Wrote an up arrow to remind myself that I have an increasing function on that interval. So f of x itself, based on my knowledge from the first derivative test, is increasing on minus infinity to minus 2 and 2 to infinity. Okay? Actually, or 2 to infinity. That's a union, but it's increasing on both of those. F of x is decreasing on minus 2 to 2. They're always open intervals for intervals of increase or decrease. Okay, let me do example 60 in a different video.